Assalamu alaikum everyone. So in the last lecture we have completed the insulated cables. Now we'll try to do some numericals based on the different techniques on the cables. The first one is, it is related to the capacitive grading, not intersheath grading, sorry. So a single core lead covered cable is to be designed for a 66 kV to earth, that is the phase voltage. Its conductor radius is 0.5 centimeter and its three insulating materials A, B and C have the relative permittivity as 4, 2.5 and 4 with maximum permissible stress of 50, 30 and 40 kilovolt per centimeter respectively. Determine the minimum internal diameter of the lead sheath. Also discuss the arrangement of the insulating materials. So in this case, sorry, it is the capacitive grading. It is not regarding the intersheath grading, because in case of intersheath grading we are using the material of the same permittivity of the same length. In this case, what we do, we'll first calculate the product of permittivity and the stress, that is E into G max. For product A, for dielectric A, it will be equal to 4 into 50, that is 200. For B, it will be equal to 2.5 into 30, it will be 75. And for C, it will be equal to 4 into 40, it will be 160. So we know that, like in case of the first case where we see that we are using the dielectric material whose permittivity is maximum, we are using close to the surface, and then the other ones will use as per the descending order their permittivities. In this case, in the previous case it was given that G max is same, but in this case G max is different. Here also you will see that if G max is same, you will see the same pattern, that whoever has the highest permittivity, that has to be kept close to the conductor. But in this case, since the Gmax are different, we have to take the product of the two. So here A is to be kept near to the surface, then it is C whose product is 160, which is greater than 75, and then B. So the arrangement will be A, C, B around the conductor. That means we have to first kept A close to conductor, then over A we have to use C, and then B. We know that this G1 max will be equal to Q divided by 2 pi epsilon naught epsilon 1 into R, where G1 max is the electric stress of the first dielectric material and Q is the charge per unit length. Since it contains the conductor contains the charge, G2 max will have the same charge, G2 max will have the same charge, and G3 max will have the same charge. So the equation will be G2 max will be Q divided by 2 pi epsilon naught epsilon 2 into R, where epsilon 2 is the permittivity of the second material. Similarly, G3 max will be Q divided by 2 pi epsilon naught epsilon 3 into R2. This equation will be for the product for the dielectric material A, this will be for C, this will be for B. Now equating these, or we can say, we can simply calculate these equations in terms of Q. That means Q will be equal to 2 pi epsilon naught E1 R G max. We simply multiply this G max by this, we will get the Q. Similarly, we can multiply this G2 max into this, we will get this equation, and finally this equation. Here we can cancel out 2 pi epsilon naught, 2 pi epsilon naught and 2 pi epsilon naught. We are left with E1 R G max, E2 R1 G2 max, E3 R2 G3 max. By taking the first two terms, that is R1 divided by R will be equal to E1 G1 max divided by E2 G2 max. That is given here. E1 G1 max is already calculated here, that is 200. E2 G2 max is also calculated here, that is this. In this case, the second material is the C1. So 200 by 160 is given as, so therefore R1 is equal to R times this multiplied. R is already given as 0.5 centimeter. So 0.5 into 200 by 60, it will come out to be 0.625 centimeter. Similarly, R2 by R1 is given by E2 by E3, G2 max by G3 max, it is 160 by 75, that is given as R2 is equal to 0.625 into 160 by 75, it is equal to 1.33 centimeter. That's okay, but we are asked to find out the diameter of the sheet. So that can be calculated by from this equation. V is equal to 66 R G1 max ln of R1 by R plus R1 G2 max ln of R2 by R1 plus R2 G3 max ln of capital R by R2. Earlier this when we have calculated the voltage equation in terms of these parameters, in that case we have same G1 max is equal to G2 max and G3 max, and we take it out in the bracket. But in this case we have different values, so we have to multiply this G1 max to their or G2 max, or in general G max to their respective terms. So finally here we are given the known values, that is this is known, this is known, this is known, all quantities known. In this equation only R is unknown. From this R can be calculated as 3.767 centimeter, D is equal to 2 R, that is 7.534 centimeter. Again similar question, slightly different, but this is where we use the same dielectric stress in every material. Determine the operating voltage of the single core cable of a 2 cm having the three insulating materials of permittivities 5, 4 and 3. The overall diameter of the cable is 5 cm and the maximum working stress is 40 kV per centimeter. Compare the operating voltage with the voltage if the cable were not graded and the material with same working stress was used. It's very simple. This is again for capacitive grading. In this case, since 5 is greater than 4 is greater than 3, that means we are using 5 very close to the conductor, and then 4 and then 3, descending order. We know for capacitive grading E1 R is equal to E2 R1 is equal to E3 R2. This can be shown by that equation where we have already used. This is this equation where we have got this one. It is actually this equation, E1 ER1 R is equal to ER2 R is equal to ER3 R. I have written here it is E1 R is equal to E2 R1 is equal to E3 R2. By taking the first two, E1 R1 is equal to E2 R1, E1 R is equal to E2 R1, which implies that R1 is equal to E2 by E1 into R. Similar, from here we can get the value of R1, which is equal to 1.25 centimeter. Similarly, R2 can be calculated by this equation, it is equal to 1.67 centimeter. And finally, voltage. This equation I was telling about just before, because in this case Gmax is common to all the materials, so it can be taken outside this brackets. So V is equal to Gmax R ln of R1 by R plus R1 ln of R2 by R1 plus R2 ln of R by R2. So V is equal to 40 and the values are given. It comes out to be equal to 50.36 kilovolt. So this is the voltage when we grade the cable. Now let us try to find out the voltage without grading. That will be equal to V G max R ln of R by R. That is equal to 40 into 1 into ln of 2.5 by 1. That is equal to 36.65 kilowatt. You can see the difference here. The operating voltage can be up to 50.36 kilowatt without exceeding the G max. Here it is only 36.65, which can exceed the G max. So you can see the ratio, that increase in the operating voltage for the same is 1.374, that is 37.4% increase. Let us try to do some objectives on the same topic so that it becomes clear. Okay. A single core cable 1 kilometer long has a core diameter of 0.5 centimeter and diameter under sheath 2 centimeter. The electrical permittivity of the insulating material is 3.5. The power factor on open circuit is 0.05 and the supply voltage is 11 kV 50 Hertz. Determine the capacitance of the cable, the dielectric loss, charging current per conductor, and the equivalent insulating resistance. It's very simple. C will be equal to 2 pi epsilon r, epsilon naught divided by ln of d by r. All the values are given. This is 3.5, this is actually 4, and this is 1. Sorry, this is 2. 2 divided by 0.5 will be equal to 4. It comes out to be 1.40 into 10 raised to power minus 10 farad per meter. Multiply it by the length of the line. It will be equal to, what is the length? Length is 1 kilometer, that is 1000, will be 0.14 microfarad. This is the capacitance. This is the part 1. Part 2 is the charging current. Charging current will be equal to V into omega C, where V will be the phase voltage. In this case, this 11 kV is the line voltage. So 11 by root 3 into 10 raised to power 3, that is with voltage. Omega is 100 pi into this capacitance. It comes out to 0.28 amperes. Now dielectric loss. It is given as power factor on open circuit is equal to 0.05. But we know that this cos phi is equal to sine delta. This also we have we calculated last time, because these two angles are complementary angles. So cos phi will be equal to sine delta, that is equal to 0.005. So in this case delta will be equal to 2.866 degrees. So PC or dielectric loss will be equal to V square omega C into tan of delta. By calculating it, where this V will be again the phase voltage, that's 11 by root 3. It comes out to be 88.8 watts per phase. So for 3 phase it is 266.4 watts for all the 3 phases. So Ri will be equal to V square by PL, this dielectric loss, because this also loss can be calculated by V square by Ri, but we have already calculated PL. From here we can calculate the Ri. So V is again the phase voltage, 11 by root 3 into 10 to the power 3 square divided by this per phase, this dielectric loss. It will give us this insulation resistance. This comes out to be equal to 0.454 mega ohms. One more, a 110 kV single core coaxial XLP insulated power cable delivering power at 50 Hz has a capacitance of 125 nanofarad per kilometer. If the dielectric loss tangent of XLP cable is 2 into 10 raised to power minus 4, then the dielectric power loss in the cable in watt per kilometer is. It's very simple. You just have to use the formula. PL is equal to V square omega into omega C into tan delta. Since this is given as loss tangent, that means this is tan delta. Tan delta is given as 2 into 10 to the power minus 4. That's why I have written here 2 into 10 to the power minus 4. This is tan of delta, and this is the capacitance. It comes out to be 31.7 watts actually per kilometer. Since it is write it as per kilometer. So but the options, you don't have to either review it, because it is asked there in terms of this. One simple objective: the charging current drawn by the cable lags behind the voltage by 90 degree, leads the voltage by 90 degree, leads the voltage by 180 degree, none of the above. Since this is a charging current, it's a capacitive current, it leads the voltage by 90 degrees. That means this option is very correct option. The last one, in a cable of conductor diameter D and an overall diameter of the dielectric D, the maximum dielectric strength. We know that the maximum dielectric strength occurs at the conductor surface, and Gmax is given by V divided by R ln of this D by R. But it is given here, we are asked in terms of diameter, so I can write it as this is 2R into 2, that is equal to twice V divided by D ln of, I can write here 2 into 2 twice D by D. This will be the equation. So now just see what are different options. Occurs at a conductor surface, that's okay, we know that it occurs at the conductor surface, and is proportional to d. But here you will see that it is not proportional to d, it is only proportional to v. It is inversely proportional to this d, and we cannot say inverse proportion because it is non-linearly related to this. Occurs at the conductor surface and is proportional to 1 by d. That is here, that is, it is okay. That's why I have written it tick here. Occurs at the middle of the conductor, this is wrong. Or occurs at the outer surface, it is minimum. So this is a right option. Thank you. I hope you understand all this. If there is any problem, any question regarding the theoretical part or on objective or on question, please let me know. I will help.